Hello everyone, today we are going to create the robot out of scratch. We will create the URDF, visualize it in the RVIZ, and we will also create robot in the gazebo and we will drive it using the teleoperation. So first of all we have to create our workspace. Go to your home directory and create learn ROS2 underscore workspace. This is going to be our workspace in which we will create a package that is src, and inside it we will keep our packages. So how do we have to create the ROS package? Let's ask the Google. ROS2 package create, and here is the official documentation. We can go through it, and there are two main types of ROS2 package. One is the m&cmake and the other is the m&cmake Python. Each build type has different structure, and now we are going to use the m&cmake, and this is the command to create the package. This is the package name, this is node name that will be created as well, and we can keep the name of our choice. So open your terminal, go inside your workspace, that is learn ROS2 and src, and here we are going to paste this command: ROS2 package create -- build type and m&cmake, and then the node name. Our node name should be my name, and the package name should be like my first package. Yeah, that's it. So it has created the package here, you can see it. Okay, inside the package, and we are going to open it in the VS Code. Alright, this is our package, and it has several files. src, which has the node, my node that we have just created, and the include file has another folder as well. And in the this is the cmake and the package.xml. Here we are going to create a folder that is URDF, where we are going to keep our URDF file. Okay, so inside that folder we are going to create the URDF file that is my robot dot URDF. So this has the extension .urdf. In these tutorials we can also find how we can create the URDF file in here. Okay, so it has some example URDF that we are going to visualize. So here it is the syntax. This is the XML file, and we declare it in the first line. Then we initialize the arguments robot, and then we give the name my first robot, and inside that we define all the description of the robot. So in this example we have just one link that is starting from here and ending in here, and then inside it there is the visual, and the visuals has the geometry which contains the cylinder of length 0.6 meter and the radius 0.2 meter. So let's copy this and paste it here. Now we have to visualize it. First we will see how does it launch. So here is the tutorial, here is the example to launch the file. Okay, it is providing the path of the URDF file in here, and this the package that is using is the URDF tutorial, and this is the launch file. So we are going to use this command. We will first have to go inside the URDF, hit enter, and then ROS to launch URDF tutorial display launch, and the model colon equal the model name, which is in our case myrobot.urdf, and hit enter. So here it is the first link that we have in our URDF file. Okay, so this is the joint state publisher node. So it currently has 0 joints, so this is displaying nothing here, and it is the cylinder of 0.6 length and the radius is 0.2. so if we like try to change it and press Ctrl C to kill it, and I can launch it, you see there's a difference. Here, come down, we are adding some other links as well. Then we join these two links using a joint here. So let's say we are going to add another link. This should be the box. So the box does not have the length and the radius. It has 3 dimensions x, y, z. As this is the syntax to call a box. So we will copy this and come in here and paste it. So this is the x dimension, this is the y dimension, and this is the z dimension of the box. Okay, so now we are going to join these two links using a joint, and we declared the joint type, which is the fixed, and the parent type, parent link, that is the base link in our case, and the child link is the second link that we have just created. Okay, so the same method we are going to create the joint. Alright, so this is our first joint that we have just created. The box link that we have just created is inside the cylinder. Okay, so the base link is too big and the second link that we have just added is inside it. Okay, so we can we like change the location of this? Oh yes, sure. We will come down and there we go. It has defined the origin. So this origin defines the location of the child frame with respect to the parent link frame. Okay, so we'll just simply copy this and paste it here, and we can also like revert back to 0.2. So there you go. So the same fashion we can create a whole complete new robot, and this is the file of the robot that we can utilize. So in here we can also see some materials name and the color as well. So this is the RGBA as the red, green, blue, and the A is the transparency or opacity of the link. We'll copy this and replace this using with the new one, and we will relaunch this. There you go. So it has a base link and 2 child link as well, and we can also visualize this using the TF tree. There's the base link, and there's the left leg, there's the right leg as well, and in the frame this is the tree, and we can also like hide and visualize the axis. So to bring some joint in here, we will try to change this by ourselves. We will write here continuous and relaunch this, and there we go. We have this joint in here that we can move. Okay, so the default axis of rotation is the x-axis. We can also change this as well. we will write an extra parameter which is the axis. So we want it to rotate about the y-axis. Okay, so we will set y to 1 and relaunch this again, and now its rotation will be different, right? Now it is rotating about the y-axis. So there are 4 types of joints: fixed, continuous, revolute and prismatic. The revolute is will be setting some limits. The continuous is just like the wheel, it has no limit of rotation, and the prismatic is the linear joint, which also have some limits as well. Here you can see there are 3 types of joints: the continuous one and the revolute. Revolute will have some limits like effort, lower limit, upper limit and the velocity. And in the prismatic, it is the linear joint and it also has some lower and upper limits. Okay, in the continuous there is no limit. The continuous is the wheel of the vehicle. Besides this visual feature, the link has another feature, that is collision, and the collision ideally should be the same as the visual is. And to add the collision, we will just add the tag collision just under the visual, and it will have the similar properties as the visual have. And after the collision, there is an extra property, that is the inertial property, that how does the link or how does the robot behaves in the actual physical world, and upon application of the force, how does it behave. This property is handled by this inertia. Okay, in this inertia we specify the mass and some inertial components I, x, and these are the 6 components that we specify. And this is actually a matrix, that is the inertial matrix, and we have to calculate this matrix and specify the value in here. And this was all about the introduction of the URDF file. To clean up our URDF, we use Xacro. Now in the Xacro we can specify the property, and we can also use something like function, and this will make our URDF file look very cool and simpler. And we can also utilize the mathematics in this. Okay, we'll remove every link, and in here our robot name is my first robot. Alright, in here we are going to declare the tag of the Xacro. Alright, so in here we are going to create our robot body, and now we are going to add some properties. We are going to create the base link, and we have to define the property of the base link like width, height and the length. So equal and the name of the property, that is base width, and the value 31. This is the width of the base link, and we will copy it. So these are the properties of the base link. Now we are going to create the base link. Now in here we have to utilize these properties. Okay, so we can call these properties by using the $sign and then curly braces, base length, space, here should be the base width, and space, here should be the base height in the Z. Alright, so let's visualize it. This is the base link, and so here you can see the origin of this base link. So now here we have lifted up the origin. So let's see what it shows us. Now we have lifted up the body, but the origin is same. There you go. The origin is at the same place, but the body is lifted up. We have just changed the body origin. Now the same fashion we will add some other properties as well. So now here is the check of visual enable. So visual is not enabled now, so there is nothing. If I enable the Boolean, there is a box, okay, and if I enable both, there will be the same box, okay. Do you see there is the Boolean and there is the visual? So our first link is near to complete. So now what about the inertial values? And now we have to add the inertials. For that we are going to use the macro function. Okay, in here we can define the macro function like this. The Xacro has this function macro, and the name of it is box inertia, and the parameter that it takes is the mass, width, height and depth. And in this tag inertial there is the specification of the origin. We are giving some rotations in here, and we are specifying the mass in here, and these are the formulas to calculate the inertial values of the box. Alright, now we are going to call it under the Boolean like Xacro colon the name of the function, that is box inertia, and space m, and m is the 5, and the width is base width, depth is base length, and the height is base height, and we can close this using this tag. Alright, now this has inertia as well. We can visualize it again, so this is completely visible. Now we will include some other links as well. And now this is the coaster wheel. The coaster is here, and the link, as you can see, so it is using this sphere command. So this sphere just has the radius, and we have defined the wheel z off, that is here, and in here we are calling the sphere inertia, that is here in this, and it takes two parameters, that is one is the mass and other is the radius, and this is the formula that is it is utilizing, and in here we are calculating the radius. And this is the joint that is also fixed. And here is the wheel, here is the coaster wheel that is very small. Okay, If I disable the TF, you can see it here. And now we are going to add the wheels. So for that we are going to use the macro function again, and this is the macro function that has the name wheel, and then it has the parameters that prefix x reflect and the y reflect, and the prefix is here, and it has rotated the given the rotation to the origin, and then it is utilizing and the geometry is the wheel radius and wheel width that is defined up here. Okay, we can also change it, and cylinder inertia that is here, and cylinder inertia takes mass, radius and height. So we have mentioned it, and this is calculating the inertial values, and this is the joint that is continuous and with respect to the base link, and this is the formula that to calculate the origin. You can also add simple rotation, you can also add simple values, or you can also do hit and trial. So here is the function ends, and now we are going to call it. If we run it now, it won't display any wheel. Okay, it is not displaying any wheel because we are not calling this function anywhere. And now we are going to call this function like this. So Xacro wheel, the drive wheel left. Okay, this is the prefix, and reflect is here and y reflect is here, and we are giving the sign, some sign to it, and this is the wheel right. Okay, we are saving it and calling it, relaunch it. There we go, there are the wheels. If we now rotate, wheels are spinning. Alright, we can also change the material from here. And this is going to be the white. Alright, and these are the gray. So now we do not want to use this package to show the URDF in the RVIZ. We want a launch file that is inside our package. So for that we have to make several folders in this package. So first we will make the launch folder, and there should be another folder that will be containing the RVIZ configuration file. So this should be the RVIZ, and now we have to include the RVIZ configuration file in this. So for that we will launch this again, and we are going to utilize this RVIZ file, save config as. We will go to our package, that is learn ROS2, and in this RVIZ we are going to name it like config.rviz, and this file is saved inside our folder. If we open this is config.rviz, so we have the configuration file. Alright, we can close it, and now we have to create the launch files. Create new file and name it display.launch.py. so this will be displaying in the URDF in the RVIZ, and one more file that will be gazebo.launch.py. so this will be launching the URDF in the Gazebo. So now we have to build this package. We haven't built it yet. And one more thing that we have to do it before, these two are the launch file, we will make it executable as well, so that the system can detect this. These are the executables. Okay, so now we have to make some changes in the CMake list. We have to mention that we have created these folders, and they are inside these folders. There are some executable files as well, and we can mention these directories in here like this. We have made the launch folder, and we have made the URDF folder, and we have made the RVIZ folder, and we are saying that inside this folder we have some executable files. So we will save it, and now we'll go back, learn, and in here we are going to build the package by using the command call con build -sam link -install. And the package is successfully built. Now we will source it, install local setup.bash. So this is now sourced as well. So inside this display.launch, we have to add the code that will be launching our robot. So for that we are going to import some libraries. So these are some launch libraries that will be running our different nodes and will be launching the RVIZ as well. So this is our function. We are going to save it, and this is the package location after building, and this line is finding the package, and in this line it is finding the URDF file, and the third line, and this one is finding the config.rviz, and in here we are just launching the node that is robot state publisher node, and this keeps the track of all the body of the robot, and this joint state publisher node will be keeping track of the joints of the robot, and it is also going to give us the GUI interface of the joints. And this is the RVIZ node, and in here it is returning the launch description, and it is returning all the configuration files that we have just configured. So let's run it. ROS2 launch, as this is the launch file, and then the package name my_first package and display.launch.py. Oh yes, this is launched. That is great, and we can also move the different joints. Alright, we can now see our robot is absolutely fine with the angles, and it is also looking good. And now we are going to write the gazebo.launch file, and this is the file in which we are just importing the libraries as we have done previously, and in the generate launch description we are again finding the package and giving the path to the robot URDF, and then we are again launching the robot state publisher, and in here we are launching this time joint state publisher. We are not launching the joint state publisher GUI because we are opening it in the gazebo, so this is why we are just using the joint state publisher. And then we have to define the spawn entity, what we have to spawn in the gazebo. So we are using the package gazebo ROS, and then the executable spawn.py, and here is the arguments. Okay, we are assigning it to the we are assigning here the entity is my first robot that we have just created in here. This is my first robot, and we have mentioned it here, and the feeding it to the topic is the robot description, And in here launch description, we are just returning everything that we have defined in here. And in the execute process, we are launching the Gazebo, and these are the plugins that it is initializing some ROS plugins and ROS factory plugins, and it is launching the joint state and robot state and spawn entity. And now we are going to run this. We are going to launch this Gazebo dot launch. And there we go. Here is our robot in the world. So it looks so dull, right? We want to give some color to it. So we'll open again this. And here is our base. We want to give it some colors to it, and I will write the Gazebo reference. This is base link, and the material is Gazebo /orange. This is the material. Now let's relaunch this. And yes, this has some color. And how do I know I can write this color? Well, there is a whole Gazebo color list that we can find. ROS Gazebo material. There we have the list of different materials that we can define in here. Now for example, if we give the color to the coaster as well, like coaster, and we want to assign some different color to it, these are the colors that are available that we can assign to the coaster wheel. So let's say we want to give the blue, we will write it blue, and now relaunch. There you go. This is blue now. And you can also assign color to the wheels as well. But now I want to move this robot. Can I do that? Let's check the topics available. ROS2 topic list. So I don't see any command velocity topics. In order to appear the command velocity topic, we have to add some Gazebo plugins to our Xacro file or URDF file. We'll come down and in here we are going to add the Gazebo plugins. So these are the differential drive plugins. Okay, this is the name and this is the file name, and in here we are just defining the wheels. So this is drive wheel left joint and this is the drive wheel right joint, and the wheel separation is 0.4 and the wheel diameter is 0.2 as it was defined in here. Wheel radius, and double it and you will find the wheel diameter. And then we have defined the torque of the motor and the acceleration, and the odometry is true, and the TF is false, and the odometry frame is odom, and the robot base frame is the base link. And let's save it and run it again. Now again, see if there is the topic available, command velocity. There we go, we have the command velocity topic. Okay, we have it. So now we are going to run this robot by using a package called ROS2 run teleop twist keyboard and the teleop twist keyboard. Okay, hit enter. And now you can use I to make it go forward, K to stop, L to rotate it to right, J to rotate it to left, and you can also play with the different keys like O, U, and M, and the greater symbol. You can go forward and you can come backward. So our robot is working perfectly. And that's it for this lab. Thank you so much.